Welcome back. Today, I'm going to be going over this long form question to help prepare you for your AP Statistics exam. This specific long form question has to do with central limit theorem and also the binomial probability distribution as well. So, this question says a recent survey found that 12% of college students prefer studying early in the morning. A university is conducting a study on college students' preferences and plans to sample 100 students. Part A asks, what is the probability that a randomly selected college student prefers studying early in the morning? So for this one, we're going to generalize the sample to the overall population. And so therefore, we're going to assume that the probability that a randomly selected student prefers studying early in the morning is 0.12 or 12%. All right, moving on to part B. Part B asks what the standard deviation is of the sampling distribution. So, in general, the equation we want to use for this is going to be the square root of p times 1 minus p over n, right? Because essentially, standard deviation wants to measure what is the spread of this data, right? How many standard deviations are we away from the mean in order for however many students to be included in that group, right? That this is part of that. And so in this case, P is just the probability of one success. In this case, that's going to be 0.12. And here we're defining a success as a student who is part of that 12%, part of that group who prefers studying early in the morning. Then we have N, which is going to be the sample size or number of trials, depending on the context. Here it would be the sample size. We're sampling randomly 100 students, and so N would be 100 here. Then I'll plug in those values. So we're going to end up with 0.12 times 0.88 over 100 and all that square rooted. And that's going to be approximately equal to 0.0325. All right, part C asks, are the conditions for inference met? So what do they mean by that? Basically, what they're talking about is, are we able to essentially generalize this to the normal distribution, right? Is there enough evidence to suggest that the results are going to be approximately normal based on the central limit theorem? Well, first, I want to discuss quickly what are the three different things that we would need to test for and know in order to come to that conclusion. So the first one is randomness. So were the people in the study randomly selected? Well, I would say yes, absolutely. Because here notice that in part A it mentioned a randomly selected college student. And so that is suggesting to me that the university is going to randomly sample. I would also hope the university randomly sampled and didn't do a bad sampling method. Otherwise, that wouldn't really be a very good study at all. So I would hope so. The next one is independence. And typically, we can conclude that the sample size should be less than 10% of the overall population. So, is it true that 100 students is less than 10% of the overall population of all college students? Well, considering that the population of all college students is probably a lot larger than 1,000. In fact, I think in some larger institutions, there's more than 1,000 students in any given year. I would say yes, absolutely, that's met. The 100 students is certainly a lot less than 10% of the overall population of all college students. So, yes, independence is met here. And then there's also the success failure condition, right? So, both the expected successes and failures should be at least 10. Okay, so I'm going to write all of these down. So, randomness is a check because they are sampling randomly. And then independence is also a check because 100 students is certainly less than 10% of all college students. Oh, I'm blocking that. There we go. And then the third condition would be the success failure condition, right? We need to have the expected value of successes and the expected value of failures to both be 10, or greater. So, what is the expected number of successes? Well, expected successes, or we could even do E of successes, is going to be equal to N times P, right? So, number of overall students times um, the probability of one success. So therefore, out of the 100, we're expecting 12 students to be successes, right? We're expecting out of the 100 that approximately 12 students are going to be successes, that 12 students will prefer studying early in the morning. Okay, what about the expected value of failures? Well, there's actually two ways to do this. We could do n times 1 minus p to get that it's 100 times 0.88, which is 88. Or we could notice that every student either will be a success or a failure in this context, of course. And there's 100 students being surveyed. So if the expected value of successes is 12, that means the other 88 of those 100 students would have to be failures in that case, right? So 100 minus 12 gives us 88 is another way to do it here as well. So either of these is good. Now, that said, both of these are greater than or equal to 10. And so because both of these are greater than or equal to 10, this condition is met. And so therefore, yes, all conditions are met here. And what does that mean? That means that we are able to use the normal approximation for the binomial distribution. That's what that means. All right, so going back up to part D, it asks, if a different sample size were used, how would it affect the standard deviation? Okay, so going back to the equation for the standard deviation, that's right here. And so if we had a bigger sample size, that means that n, the denominator of this fraction, would be either larger or smaller, right? So basically what they're asking here is what if we made this n value larger or smaller than it already is? Would that make the standard deviation larger or smaller? Or would it remain the same potentially? So there's a couple ways to do this. We could think about how this would work in theory, and I will discuss that as well, or we could even just look at the equation and decide what's going to happen. Let's say that n was bigger, right? Let's say we chose to sample 200 students or 300 students or some number that's more than 100. Well, in that case, the denominator of the fraction here will increase, and that's going to cause the standard deviation overall to decrease, right? And so therefore the standard deviation that we would have or that we would expect to get would be less, right? We would expect less variety, essentially, the more people that we survey. Or if we survey less people, that would impact it in the sense that if we had less people, the denominator decreases, which would make overall the standard deviation increase. And so that's telling us that there's more variation overall if we choose less people, right? There's more different varieties of what could happen if we were to repeat this study many, many times. So basically, to make a long story short here, increasing the sample size, right, surveying more and more students is going to reduce the standard deviation, make it lower, and decreasing the sample size, so surveying less students, is going to increase the standard deviation. Now, I want to talk about, okay, well, how come that is? Well, based on what the the central limit theorem states, we know that the larger and larger the sample size, the closer and closer we are to actually approaching that normal distribution. And so if we do a really, 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 really big sample, like 10,000 college students, for example, that's going to be a lot closer to the normal distribution than if we do a smaller sample. There could be a lot more variety of, of results in a smaller sample, right? And so if we think about it that way too, we would come to the same conclusion that having more students would make the standard deviation be less, and having less students would result in a potentially higher, or it would be more likely that we would end up with a higher standard deviation. All right, well, that's all for this one. If you have any questions, feel free to leave those down in the comment section, and we'll see you for the next one.